So as we just learned about in our last problem, one way to determine an unknown delta H for a reaction is to take delta H's for known equations, thermochemical equations, and manipulate those equations such as they sum up to your target equation. Another way to do it is to use standard enthalpies of formation. So we're going to do a problem like that in problem 6.10, but part of understanding what that means is learning how to write formation equations and what these equations really mean. So I had something that was written down on your summary sheet here, right? So when you see delta HF, that's the enthalpy for a specific reaction. That little f just means it's for a specific reaction, a formation reaction. And what that means is it's the delta H for the reaction that forms 1 mole of a substance from all substances needed to make it in their standard states. So to do this, write an equation for standard enthalpy of formation. You basically use 1 mole of the substance that you want to have this equation for as the product and create it from the reactants in their elemental forms. You will have fractional coefficients to do this. Don't try to scale things up to have whole number coefficients. The concept is that these enthalpy values are for 1 mole of a substance that you're forming. So this sample problem just kind of walks through a few of these in terms of just understanding how to write these equations. So again, we want to make the standard formation equation for silver chloride. So what we do is we write silver chloride as a product, and we say, what are the elements that we make that from? Well, you make it from silver as a solid and chlorine gas. So part of this is understanding that elemental chlorine comes as diatomic chlorine gas, which means in order to have one of these, we have to have the coefficient of 1/2 there. Now, one of the things that we need to do that's part of this is introducing us to Appendix B here, because it asks us to include the value of delta HF. Okay, so what we need to do here is we need to look up these values. They're alphabetical, so we can look up silver here. So when we look up silver, we can see silver chloride. The column that we're going to be using in this chapter is the first column, delta HF values, and we can see that the value is -127.03 for silver chloride. So delta HF equals -127.03 kilojoules per mole. And in this case, we do write per mole because it is for 1 mole of product. All right, let's go ahead and run through these other ones. B is for calcium carbonate. So again, write calcium carbonate as your product and write what it's made from. Well, we've got calcium that's found as an elemental metal. The elemental form of carbon is graphite, and that's just something I want you to know, that the elemental form of carbon is graphite. I'll give you a little heads up if you forget that. Any of the values that are written on this table, if they have a 0 there, that's mean it's how you find it in its elemental form. For example, if we look at chlorine here, we can see chlorine gas is the elemental form. So if you forget, always know that this is kind of a cheat sheet for you. The elemental form of carbon is the graphite form. So carbon as graphite, and then the elemental form of oxygen is O2 gas, and we need to balance this with a 3/2 in order to end up with 3 oxygen atoms. Again, looking up the delta HF from our table, we get -1206.9 kilojoules per mole. For our last one here, we're going to have HCN, hydrogen cyanide. So hydrogen cyanide as a gas. We make that from elemental hydrogen gas, 1/2 mole of that, carbon in its graphite form, and then nitrogen gas, again as a diatomic gas, means we have a coefficient of 1/2 in front of that. Delta HF for this, again looking it up in the table, and I'm going to show you this one because I think this one is an interesting one to look at. We can look it up under carbon here. Sometimes things will be present in multiple areas, but HCN here is under the carbon section. We can see that it has a value of 135. As you kind of scan through this table, you'll see a lot of negative values. Okay? Basically, it means to form this product and make those bonds, you actually make something that's more stable. So the rest of the energy is given off. This one's unique in that it's a positive 135 kilojoules. That's kind of unusual for a positive delta H of formation. That basically means that it takes energy in order to make this product. Most of the time when you combine things together and you make new products, the delta HF is going to be negative. For example, if we look at sodium chloride, right? We looked at the video of that. We take elemental sodium and we mix it with elemental chlorine, quite a violent reaction. And so not surprisingly, the delta H for this is going to have a negative value because that extra energy is given off. So again, we'll use more of Appendix B on our next and last problem from Chapter 6 here, but part of the skill in this section on delta H of formation is learning how to write these standard formation equations.